Did I mention that? I didn't? Really? Are you serious? Look. Well, now you know. That's next week. So I'm gone. I'm out of town all of next week. Now, where is Sam? Is he? Okay. So the reason there are no classes Monday and Wednesday is that I'm out of town. But Sam is here, and he should still have his discussion section on Friday. So he will have his discussion this Friday. He'll have a discussion next Friday. Do take this opportunity to make headway on the project. I was just talking about you.
How great I am?
I told him that. Should I tell him what he promised to do? I don't know. So, first off, I know that you and I are meeting this afternoon. I think Will asked. Don't remember. Was it Will who asked when the test cases will be available? And I promised them that they'd be available this afternoon. So remind me.
Hopefully I can do that.
Shortly.
Right after class.
Yeah. The other item is that I am not here next week. So Monday and Wednesday there are no classes. You're supposed to look all sad. That's right. That's right.
Please let me teach instead of you.
Everyone's supposed to say, oh no, we really, really wanted to learn about code generation. Anyway, but you have a discussion section on Friday, and you will have one that Friday as well, on the 5th, right? So that'll be there. And that's important and useful because, as I said, the code generation project is a lot of work. Get started soon. If you have questions, do please just get started so that when you have questions, they're timely and you can take them to the discussion section early. Okay? I was going to talk about the code generation thing, but there's one other item that I do want to bring up. So let me go ahead and bring that up because it is important. Milestone 1, here's milestone 1. It's due reasonably soon. It involves code generation for a subset of the subset of C we're compiling. So it's a really small subset, but it's a hard subset. And the reason it's a hard subset is that we need to deal with functions, because just the way the program is set up, if I can't do functions, I can't do anything. Okay, so way back when, I'd created this project, and code generation was this big monolithic assignment that said, here's a bunch of programs, go generate code. And sometimes what happened is that people didn't realize, because it wasn't explicit, people didn't realize that if I don't have functions, it doesn't matter how good my expressions are. I could be generating really bulletproof code for expressions, but the compiler wouldn't work because my functions didn't work. So eventually, took me a long time, but I eventually figured that out. I said, okay, we're going to do a subset for milestone 1, which does very, very simple sorts of functions. Okay? And this subset is this small subset of C++ essentially does just functions and just enough variables for us to actually print stuff out and see if things are being done properly. Because otherwise, I could make all kinds of function calls and I'd never know if they were happening properly or not. So here, we'll have globals. So in this subset, we will talk about globals and at most one formal parameter. So we'll deal with functions that take at most one argument. And globals can be ints, chars, array of chars. So these are all the regular kinds of variables that I have. But I'm going to compile functions with at most one argument. Okay? And I can have statements, and the statements are going to be fairly simple. So the statements will be one or more assignments and procedure calls. That's it. So we won't have loops, we won't have while, we won't have for, we won't have if. So function bodies will be fairly simple. Assignments will be simple. The left-hand side is going to be a scalar variable. We won't have arrays. Right-hand side is a scalar variable or a constant. Okay? So really, really simple. So this means that we don't have any references to array variables for this assignment. A procedure call takes at most one argument, which is of type int, char, array of int, array of char. Okay? But of course, I don't have any references to arrays. So the only place where this could be, where interesting things could happen, is with an array of char, which I can print out. Expressions, scalars, constants of type int or char, and string constants. So no operators, no array references, or function calls in expressions. But I can have function calls as statements. Wait a second. Yes, that's right. Assignments and procedure calls only. So this milestone should get you at least sort of the bare bones minimum of expressions and function calls. I'm sorry, simple assignments, expressions, simple assignments, function calls, right? So really, really simple. Now, bear in mind that I think 10 days after this, you'll have to have code generation for the entire C++ language working with array assignments, with array references, with for loops and while loops and return statements and function calls and expressions, the whole works, okay? So when you're designing your code generation, keep that in mind that all of these things will have to be extended to deal with the rest of the language. Okay, initially, we're just getting the scaffolding right, just getting the scaffolding of function calls, because that is the most complex part of the code generation, because there's a handoff from the caller to the callee. Caller says, hey, here's some arguments, and here's the return address, and the callee gets those and works with them, and then has to return to the right place and so on. So this milestone is not that, it's not like you have a great deal of time for it. Right? I think it's due on the 10th. So you have less than 2 weeks for it. Again, do get started soon. And that's where Sam's discussion sections will be useful. Here we go. So this talks about how print routines will be used. Testing your code. So you can obtain the expected output for a test case by compiling with GCC. Right? So C++ is a subset of C, which means that any legal C++ program is also a legal C program. Okay? So you can take a C++ program, compile it using GCC, run that code, and that'll show you what the expected output should be. Now, C doesn't have print int and print string as primitives or as library routines. So you'll need to supply those. Put that in a separate file. Compile to a .o file and then just, you know how to make that work, right? Link those in together. So can you handle that? Yeah, you can handle that. All right, so I'm surprised that I hadn't mentioned that there's no class next week. Anyway, I know we're all disappointed by that, but life is what it is, so we'll have to be strong and march on. So let's be strong and talk about code generation. We talked about this last Wednesday. Really, really quick recap. 3-address code looks like machine-independent assembly, except that the code, the program, the code that your program generates will be a sequence of these 3-address instructions which in this case looks sort of kind of like C code. Well, of course, this particular piece of code has all sorts of typos in it, all sorts of typos. And if you're bored, you can kind of go off and find all the typos. You know those puzzles there, find all the differences between these two pictures, find all the typos in this code. It'll entertain you for a little bit. Looks sort of kind of like C code. The big difference is that you're not allowed to have more than one operator on the right-hand side. And what we will do is look at a simple 3-address instruction set. This is a little different from the document that I showed you. So you can have differences. You can pick and choose. This one, the big difference is that this assumes that you have a much richer set of base types. So it makes sense to have instructions that convert from one type to another. Okay. Now, in C++, some conversion is necessary, but it's fairly minimal. And in fact, they're only there to bring to your awareness that sometimes conversion does need to happen, and the specific conversions that you'll need to deal with. So keep this in mind, because sometimes people forget that the specific conversions you'll need to be aware of and deal with are conversions between ints and chars. Okay, so going from a 1-byte char to a 4-byte int requires sign extension in one direction, truncation in the other direction. Okay. There was a point where I had thought about throwing in floats, but they're more trouble than they're worth, so I decided not to.
Real quick question.
Uh-huh.
It looked like int arrays are supposed to be compatible with char arrays. Is that not true?
Int arrays are not compatible with char arrays.
Boy, I guess I did that wrong if I read.
Uh-oh.
It's supposed to be compatible.
Well, let's find out.
Simple types are compatible with the arrays.
Yeah.
Well, I mean, I was surprised by it too, but I thought I read specifically that was the case.
So that's a state, an issue of fact, and we can verify that offline. My recollection is that int arrays are compatible with int arrays, char arrays with char arrays, but not one way or the other. So here's the reasoning for that. We're accustomed to being able to assign a char to an int variable, a scalar variable, or an int to a char. And that's where the compatibility point comes in, right? That a char, I want to be able to take a char value and assign that to an int, and potentially some conversion may be necessary, some representation conversion, in this case sign extension, but not more than that. With arrays, though, I don't take an int array and assign that entire array to a different int array. Okay, I don't take a char array and assign that to an int array. So arrays, so there's no question of doing assignments between arrays. The one place where I take an array and do something with another array is in an argument passing, parameter passing. So I can have a formal that's an int array, and the actual is going to be an int array, and my type checking has to work. Okay, but in the implementation, what will happen is if I have an int array, and I'm passing it an int array as an actual parameter, what I'll pass is the pointer, right? So that assignment of the actual to the formal will work because I'm not copying the array. But I can't make that work if I pass an int array in place of a char array. You see what I'm saying? So the whole point of the compatibility thing is to say if I have scalar variables and I can do some kind of promotion or demotion, I can do a format conversion. When I'm doing argument passing, I don't have that. And so I want, if the formal says int array, the actual has to be an int array. If the formal says char array, the actual has to be a char array. Okay? Amr?
The elements of the arrays are compatible, right?
The elements of the arrays are compatible. So if I have, let's say x is an int array and y is a char array, then I can say x sub 5 equals y sub 7. That assignment is okay. And your compiler will do the appropriate format conversion. It will generate code to do the appropriate format conversion rather. Okay? Format conversions involving floats become tedious. There's nothing fundamentally difficult about it. It's just there's a lot of architecture-dependent stuff that you have to kind of read up on, because the bit-level representation of floats is quite a bit more complex than, and that's why we don't have floats in the language. Here's how 3-address instructions get represented in the compiler. Okay, so what your compiler does is it's taken the token sequence, constructed a syntax tree. We start traversing the syntax tree, and as we're traversing the syntax tree, you'll see me making this gesture, traversing the syntax tree, and that suggests a top-down traversal. It's actually a bottom-up traversal. It's a post-order traversal. Okay, and the reason it's a post-order traversal is that, just to give you one example, if I want to add x plus y, then I need to evaluate x first, evaluate y first, then do the addition, which means that the code I generate should be code to evaluate x, code to evaluate y, do the addition. So it's a post-order traversal, okay, bottom-up. So what the compiler will do is it'll generate a sequence of 3-address instructions in the form of a list or some such data structure, a function at a time. Okay, so for each function, it'll create this list of 3-address instructions. They will look like this. Each 3-address instruction will look like this. It'll have potentially have pointers into the symbol table entry. It'll have pointers into the symbol table where appropriate. So your 3-address instructions are structs that potentially have pointers into the symbol table. Okay, so if I have an expression x plus y, there'll be a struct. There'll be an add instruction. Okay, let's take this one, x equals y plus z. So the operation field tells me what kind of operation this instruction is about, and there's a pointer to the symbol table entry for y, a pointer to the symbol table entry for z. These are the two source operands. There's a pointer to the symbol table entry for the destination operand. And in our case, we don't need basic blocks and stuff, so it's a linked list, whatever next pointer, maybe a previous pointer if you want to keep a doubly linked list, and so on. All right? So this is what a 3-address instruction looks like, and you create a list of these instructions. Then you take this list of instructions, and for final code generation, you take this list of instructions and you just traverse the list of instructions, and each 3-address instruction expands out. It's almost a process of macro expansion. It expands out into some number of MIPS assembly instructions. Those get printed out. Okay? Now, for debugging purposes, you will probably want to print out your 3-address instructions as well. So you can it's not hard to see how you take a struct like this and print out something along these lines. Okay. Your SPIM code allows comments, the SPIM assembly code. So you can print out the SPIM assembly code that you're generating. In comments have the 3-address instruction that you're printing, that the SPIM code comes from. If you want, in comments, print out the source line that it came from. You can do that, right? What that would entail is you keeping track of a little bit more information about the current source line. But your error handling, in order to do error handling, you already have the current source line sitting around in a variable somewhere. So if you want, you can spit that out into a comment. That's not terribly difficult to do. Okay, so here's how we will approach code generation. Function prototypes and globals, we'll save information in the global symbol table. Okay? When I see the function definition, the actual definition of the function, we'll save information about the name, return type, arguments, and so on in the table if it's not already there. You may have seen a prototype and saved that information already. Anyway, then we'll process the formals, we'll process the locals into the local symbol table. So now I come to the body. I'll process the body. I'll construct a syntax tree. I'll traverse the syntax tree. I'll deallocate the syntax tree and the local symbol table. Okay, so then I'll go on. So then once I'm done with this, I'm back at global scope, and I go back and I process the next set of globals. Okay, so I'm working this a function at a time. present this code generation discussion in terms of traversing a syntax tree. It's a recursive traversal. Sometimes people find that they're running short on time and constructing the syntax tree is much too much effort, and they'd rather not. And that's okay by me. I mean, I find it convenient to do the syntax tree because I can look at the tree and see if there's a misstructuring of the tree itself. And I find that easier to identify problems there than to figure out stuff at the assembly code level where there's a lot more kind of finer grained detail, and that makes it hard to see the full clean picture. But again, I'm not going to be checking that there's a syntax tree. I'm just saying that it's convenient to do so, to have one. So my discussion is going to be presented in terms of traversing a syntax tree and generating code. So it's a recursive traversal. So you look at each node in the tree as you're traversing it, and the node type determines what you do with that node, right? So the node type is, when we were discussing syntax trees, we talked about this. The internal nodes specify what computation is being performed. So for expressions, the internal node is the operator, something like plus or minus or times or unary minus or whatever. For statements, the internal nodes represent what kind of statement it is. Is it a for? Is it a while? Is it an if? And so on. And then the children of the node are the code that operation is being applied to. So I generate code for each node after I've processed its state. Okay, so for example, if I have a while expression, so suppose this is what my code looks like. Okay, this is the source code fragment. What I'll do is this will translate into syntax tree, a syntax tree fragment that looks like this. While the tree for E and the tree for S. Okay? So this is what the syntax tree corresponding to this source fragment would look like. What I would do with this for 3 address code would be to recursively traverse the tree. So I do a post-order traversal. So I'd have the code for E, for evaluating E, the code to evaluate E. Then, so this guy returns a list of instructions that will evaluate E. Okay, so this is what I get back from that traversal. There's the code for S, which I get back from the traversal for S. Then I glue them together. So the way I glue them together is, in this case, let's see, do I have other colors? Yes, I do. So the way I glue them together is to say, okay, this is a while loop. So let's think of what my code needs to do to execute a while loop. I first need to evaluate the expression, and I have the code for doing that. If the expression is 0, then I need to bail out. So I'm going to have some sort of a if go to over here. That's what will be inserted when I'm processing this node. So that corresponds to generate code for each node. The traversal for the expression E has no idea that it occurs in the context of a while loop. So the code that is produced over here is simply the code for evaluating E. The code for S that was produced by traversing S has no idea that it's in the context of a while loop. And it shouldn't. There's no need for it. So this code is simply the code to execute S. It's when I now start doing the while loop that I say, okay, I can take the code for my children, stitch them together with any additional instructions that are necessary to make that guy work. So now I introduce an if, take the value for E. If it's 0, jump out of the loop. Otherwise, fall through, execute the code for S, and jump back to the top. right? That's what, so this, processing that node introduces this instruction and this instruction. And now I glue this whole lot together into a list, and I pass it back up to my parent. And maybe this while loop occurs in the context of, maybe there's an if node up here. So that if node, when it's processing, the if node takes this list and glues additional code around it as necessary, and so on and so on. Okay? So that's how the big picture of the code generation is going to work. Recursively traverse the tree. You get back lists of instructions from each subtree. Then I come back over here, and I take those pieces that I've gotten, and I glue them together with any additional code necessary for that for that syntax tree node. Okay? Questions? Okay. So here's how, this is just mock-up of simple code. Here's a routine in the compiler for code generation for a statement. So I give it a syntax tree node, and I do a switch, right? So depending on what type of node it is, I do some stuff, and then I break. Similarly, I have a code gen expression. I take a syntax tree node, and based on the type of the node, I do some stuff. Whoa, animation, wow. Okay, so I recursively process my children. So I need some auxiliary routines in the compiler to make this recursive traversal thingy work. So let's discuss these quickly. And then on Wednesday, we'll have a chance to actually dive into the details. Here are the things that I'll need to do. I will need to create temporaries. Remember temporaries? If I have complicated expressions, I need to flatten them out into simple expressions. So I need placeholders. I need locations where I can store those values. Those are temporaries. Well, I need to create temps. So what a new temp will do is it will take a type name, and it will create a temp of that type. And at this point, when I'm generating tree address code, I don't need to actually go ahead and allocate space for it. I just need to set it up so that when space is being allocated, that will cause space to become allocated for the temporary as well. So this guy will take a type name, create a temporary of that type. So it'll malloc of a little symbol table node, set the name of the temporary accordingly. And we discussed that briefly last Wednesday. Set its type to be T, stick it in the symbol table, and then return a pointer to that symbol table node. Okay? I'll need labels because I need to be jumping around, and as this example shows, I need to be creating labels. And there's this global requirement that every label has to be unique, right? So you can think about how one can do that. That's not terribly complex. Just have a global counter. So it returns a new label instruction. So your labels are going to be in the list of instructions, and you can point to a label and say, that's where I want to jump. So it's just a label statement. Statement type is label. Just doesn't generate any code, but it does. You can refer to it. And I need to create instructions. I need to create tree address instructions. Okay, so we talked about what instructions look like. That's what instructions look like. I need to create one. The way I create one is to say, here are some arguments. Here is the type of the instruction. Here's the operand 1. Here's operand 2. Here's operand 3, whatever. So new instruction takes a bunch of arguments, fills in the instruction type, and then returns a pointer to the result. Okay? So you can probably figure out what these need to look like, but let me just kind of put it up just to be quick. So how do I create a new temp? Well, I malloc it up, and strictly speaking, I should check whether I ran out of memory or not. That's always a good habit, but I didn't have space for it on the slide, so I elided it. Create a new name, define its type, put its scope to be local. I indicated that the scope is local. But of course, it's I mean, depending on the specific details of your symbol table implementation, it might suffice to just take this thing and stick it in the local symbol table. Maybe that's enough. Okay. You do want it in the local symbol table because you don't, okay, if temporaries went into the global space, then they would use, they'd consume space even after the function that the temp belonged to was long gone, and that's just aesthetically not pleasing. All right, so new instruction. Here's what a new instruction looks like. I've taken operation type source1, source2 destination. I malloc up an instruction. I set its operation type. I set the field to return the instruction. So that's essentially what these guys will be doing. Okay. Here's how I generate code for a function. Conceptually, here's what the code for a function needs to do. Okay. Remember, when we talked about runtime environments, we discussed the calling sequence and the return sequence for a function. So the calling sequence, actually for a function call, the calling sequence is a sequence of instructions that has the effect of setting up all the arguments and stuff and getting the callee to begin executing. The return sequence is the opposite, right? The callee sets up the return values and such and then returns control to the caller. So let's think about what's entailed in the calling sequence. The caller executes some code to put the actual arguments where the callee can find them. So there's some convention that allows the callee and the caller to agree on where the arguments are to be found. For our purposes, the calling convention that we'll be using is that the arguments are going to be passed on the stack. Okay? So the caller evaluates the arguments, puts them on the stack, then transfers control to the callee. When control enters the callee, here's what the callee needs to do. The callee needs to save some local state, right? Save the return address, which is in a return address register. Maybe save the old stack pointer or the old frame pointer, whatever. Then it needs to allocate its stack frame. Once it's allocated the stack frame, now it's ready to start computing. So it starts computing the body. So there's that initial setup stuff, which is save some state, save the return address, frame pointer, then allocate the stack frame. That needs to be set up once the function is entered before we actually start executing the body of the function. So we begin with an enter f. And f is a pointer to the function's symbol table entry. What information will that symbol table entry contain? What it will contain is how much space I need for my local variables and temps. Okay, because I need to allocate space for my locals and temps before I start executing my body. So there's a glitch over here, right? Because I don't know how much space my compiler needs to allocate for a function f in the stack frame until it's actually done code generation for the body of f. Because it's only once I've done the code generation that I know how many temps I need, how many temporary variables. But I need to have this enter f at the beginning, and that's where I'll need to know how much stack frame to allocate before I start processing the body. So the way that gets resolved is that initially, I just go in and I create this enter f. So the enter instruction has a pointer to the symbol table entry for f, which is in the global symbol table, because the function name f is in the global symbol table, right? So all I know at the beginning is that the function I'm about to enter is this function f. How much space does it need? I have no idea. Then I start generating intermediate code for the function. 3-address code, okay? This is not MIPS assembly code. This is 3-address code. Now, as I'm generating intermediate code, if I need to create temporaries, if I have I plus z plus w, I need to break that up into simpler expressions, and I'll need temps. As I do that, I create new temps. I stick them in the symbol table. Once I'm done looking at the entire function, at the end, I have completed intermediate code generation for the entire function. Okay? So now I know exactly how many temps I need for this function. I know exactly how many local variables I have for this function. I know any, so at this point, I know exactly what all local variables and temps I need. Now I am about to start generating code, MIPS assembly code, for that function, right? So this is our code generation approach. Traverse the body, generate intermediate code for the node. Then when I'm done generating intermediate code for the function, now I come back and I traverse that list of intermediate code instructions and I spit out assembly code. But the nice thing is that at the point where I'm about to begin generating assembly code, I've actually seen the entire function body, right? So now I can go in and I can fill out, I can traverse the function's local symbol table, and I can compute how much space I need. Now I can generate assembly code for this enter F instruction because I know how much space I need. Oh, I ran over. I'm sorry. On Wednesday, we'll pick up over here. We'll actually look at the details of how all this is going to work. And that'll